SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering Module 2 Vapor Power System Part 1. Now in this lecture number 4, we are going to explore the following topics. First one is vapor cycle exergy analysis. Till this point of time, we have analyzed exhaustively the Rankine cycle. Now, in order to study the performance of the cycle, we want to do the exergy analysis component wise. So, important components for Rankine cycle we can think of as a boiler, and this can be modeled as a heat exchanger unit. Then we have other components like turbines, pumps and condensers. So, for these components we will try to explore what are the expressions for exergy, and in a Rankine cycle how you are going to evaluate the complete exergy analysis. Now, apart from this will almost complete this vapor cycle analysis thermodynamically, but we will try to explore other vapor power cycles that operate on Rankine cycles, but with certain differences. First one is working fluid and organic cycle. So, basically in our analysis so far, we have told that working fluid is water and steam, but there are cycles where thermodynamic cycles where working fluids can be changed and through some organic substances. So, we call them as organic cycles based on Rankine cycles. Then we have other vapor power cycles. Here also we can have a multiple working fluids, like one case we can have water, and in other situations we can have some other fluids, like some of them can be organic fluids. Then we have the steam cycle that is operated for nuclear power plants. So, Rankine cycle is almost a very common for nuclear power plant applications, where it supplies steam for the coolant of the nuclear power plant. Then we have low temperature cycles. There are certain situations like where we are going to explore, where there is a possibility of exploring energy from low temperature environment. For example, we can think of solar radiation getting absorbed in a pond, and such a things we can say solar pond. There are some geothermal fluids which is underground water. I mean in underground there are if water is considered, its temperature may be high. So, if you explore geothermal energy and in which uses water as one such working fluid, then we can use the temperature of water as one of the medium or a source of boiler. Then subsequently we have to use some other working fluids which that operates in the low temperature cycles. That means we can think of various refrigerants. The other concept that goes is cogenerations. So, this is a concept where we think of integrating two or more power generation systems for variety of applications. One such instance could be the combination of a gas turbine plant and steam power plant. Other may be some kind of steam extraction plant which can be utilized for various heating systems. So, such models they work on cogeneration systems. So, we will try to touch upon the basics of these other vapor power cycles. Now, let us go to our first topic which is vapor cycle Exergy analysis. So, before you go for this Exergy analysis for steam power systems, let us try to understand what is the concept of Exergy. So, Exergy in thermodynamic viewpoint is considered as one of the property like energy, but it has a different meaning. So, when you say energy in thermodynamic viewpoint, we say either it is available in the form of heat or work, and second law analysis says that heat cannot be completely converted to work form, which means there is some potential of that means there is a certain potential that heat can be converted to certain extent. And on top of that, when you integrate these systems with environment, then we need to view this system as well as environment together. Now, system can be considered as the best potential of work when it reaches the final thermodynamic conditions, which is certainly at the dead state. So, if you look at this particular systems, if you say there is a closed system and this system has certain boundary, we say is a system boundary, and this system can interact with the environment, and the environment condition is at pressure P naught and temperature T naught, and it can through these things it can work together. The system and environment can be considered as to work together, in which heat and work interactions is possible. Now, if you take the system and surrounding together and bring it as a combined systems, okay, and where the system and surrounding work together to produce the energy in the form of work. So, we say that the work potential of the combined system, that is WC, and that can be viewed as a rotation of a shaft or rising a weight, or it can be considered as electric energy. So, basically speaking, we are considering the system and the surrounding together and try to find out the work potential of the combined systems, and how long this work potential or work delivery can be possible when the system finally reaches to the dead state or environment. So, the potential to develop the work is known as the exergy, and other way we can view that if a dead state can reach to the system state, then we regard this minimum theoretical work as its work potential to bring the dead state to a given state. So, this view or this concept leads to the fact of finding the work potential of a given system. So, there more details are also available in the basic thermodynamic course, but here when the system is brought to the dead state and we view this as a combined systems and try to find out what is the work potential. So, this is nothing but if you say the total energy of the combined system is E, consisting of internal energy, potential energy and kinetic energy, its work potential can be expressed as the change of internal energy and the work, that means plus, that means this is the U plus PV, something called as flow work. Then the difference in the kinetic energy and potential energy, and the term that is associated with the entropy change for the combined systems. So, basically if you take this as a work potential and exergy is termed as the maximum work potential, then obviously the final term becomes 0. So, you can find out the exergy of a systems. Subsequently, per unit mass, when you say we find the exergy, specific exergy. So, this is the working formula to find out the exergy of a systems by considering system and surrounding together. Now, here P 0 subscript 0 stands for the conditions of environment, and in all our dead state situations we say P 0 as 1 bar and T 0 is 25 degree centigrades. So, this is the dead state conditions in which we are going to work upon. So, that means whatever work potential has to be calculated till this final pressure and temperature the system reaches to the dead state. Then moving further, we need to quantify the exergy by a parameter something called as exergetic efficiency. This is something similar to the efficiency which is defined in the Carnot cycle, but here little bit of difference that we need to find out. So, let us try to understand that we have a systems consisting of its boundary and it is receiving some heat Q dot S, and by receiving this heat system rejects system does some useful work in the form of Q dot U, and heat which is going to lost which is known as Q1. So, while basically speaking, so Qs would be Q1 plus Q dot. Q1 dot considers for loss and Q dot is considered as the energy utilizations. Now, if you want to find out the work potential for, so obviously when you calculate the efficiency of this particular systems, so it is nothing but the ratio of Q dot U by Q dot S, that means energy which is being utilized divided by energy heat energy which is being supplied. So, this is what we known as efficiency of this system. But if you want to find out the exergetic efficiency, then we need to find out what is this work potential for this Q means energy, what is the work potential, because this Q is not taken, has not taken into account the surrounding conditions, which is P naught is 1 bar and T naught is 25 degree centigrades. So, to considering this as a dead state conditions, if you want to find out what is the work potential for this Q dot U, we can find out this through our expressions using from the Carnot cycles. So, work potential for this Q will be 1 minus T 0 by T u into Q. Similarly, work potential for Q dot S we can write it as 1 minus T 0 by T s, and this is nothing but we get the expressions from the Carnot efficiency. So, now considering this, expressions can be now rewritten as a exergetic efficiency can now be rewritten as efficiency of the systems multiplied by another term, that is 1 minus T 0 by T u divided by 1 minus T 0 by T s, and obviously this since efficiency is always less than 1, so exergetic efficiency will also be less than 1. So, this is how you calculate the exergetic efficiency. Now, in our term we consider when we take into account a vapor power systems, we are now going to work on this exergetic efficiency. So, the components involved here are turbines, pumps, then we have heat exchanger, we have condensers. So, all these things are involved and they are considered as the steady flow devices. So, our main role for this discussion would be to find out the how you are going to define the exergetic efficiency for different components. So, we can say that there is a decrease in the flow exergy for turbines from inlet to exit of the turbines, and there is a increase in the flow exergy from inlet to exit of the for the compressors and pumps. Obviously, we are going for pumps only. So, that is increase in the exergy. Now, for heat exchanger, in our say we say heat exchanger typically model as typically analogous for a boiler, where hot steam supply exergy to the cold stream as well as the exergy is also destroyed. So, basically in a boiler what happens, heat is being supplied to the systems through some certain processes or this through the combustion products. So, thereby some exergy is being carried into the systems and exergy is being carried out by the systems. So, we are going to model that way. Now, here when you talk about the heat exchanger unit, there are two possibilities. One is the fluids mixed together, Like if you say one particular counterflow arrangement, we have a hot stream that is coming in and which is going out as a cold stream, and another channel we have a cold stream which is entering and it is going out. So, in through this process the cold fluid is receiving heat from this hot fluid, and of course, they do not mix each other, and their flow rates are also different. That means, cold stream has a different flow rate can have and hot stream has a different flow rate. But in other type of arrangement there can be possibilities that hot stream is coming and cold stream is coming and it goes as a mixed stream. That means, both the fluids are mixing together. So, we can here we can say mass balance as M1 and M2, that addition of M1 and M2 gives the M3. So, accordingly the term of for the exergetic efficiency for different components we can find out. So, here you start with an expressions specific exergy, and this specific exergy term we have to apply it for different components, and if you apply for the turbines we can find out what is the exergy flow coming into this and what is the exergy going out of the turbines. So, that is the bottom, and if and what is the actual work output per unit mass is we are getting from the turbine. So, this ratio gives the exergetic efficiency for turbines. For pumps its expression is completely reverse, because the pumps require work as a input. And now, for heat exchangers the expressions are defined through the heat carried by the working fluid of hot stream and heat being rejected to the cold streams. Here the expressions are slightly changed based on this mass balance. So, these are the working formula for exergy analysis, and in our subsequent discussions we will see how these formulas can be used to solve some problems. Then let us start with the first unit. Like in our exergy analysis, if you say it is a heat exchanger unit, in our perspective of vapor power systems it is considered as a boiler. So, in our analysis we simply said that heat is being fed to the boiler, but how this heat is being fed? To have certain insight into this particular philosophy, what we model this as it is a model as a heat exchanger unit, and in fact heat comes from a fuel and by burning like coal or some other fluids of some petrol, diesels from in IC engines, by burning this we get the gaseous products of combustions, and that enters, and it may be temperature is very high here, that enters to the boiler unit, and only difference is that of course this operates at that boiler pressure, and when it enters it gives the heat to the working fluid for this vapor power cycle, and this is nothing but your liquid water which is enters in a counter flow arrangement in this manner. So, here if you look at the boiler, the working fluid, that is water, enters at state 4 and it goes at state 1. So, from 4 to 1 its enthalpy changes and it receives heat from the gaseous products of combustions. So, this is how when you talk about the heat exchanger unit, we need to find out what is the exergy is being carried out by these gaseous products, and typically in the case of absence of data, these products of combustions can be modeled in a more appropriate manner by using air, and this is being carried into these systems. And in other side of the story is that the heat exergy which is carried out by the water from the heat exchanger units. So, the net effect will give you the exergetic efficiency, and remember while talking this analysis we still assume that dead state conditions is 1 bar and 25 degree centigrade. And the similar way we can calculate the exergy for each of the stream, and this is how we calculate. One thing is that since for this considering this heat exchanger unit, we can say that that the combustion products can be modeled as a air. if we model this as a air and you say its mass flow rate is m dot a, and remember this mass flow rate is also conserved, and side by side if you say steam is being modeled. So, m 4 that is steam that is entering and steam that is leaving, they are same, and we say that is m dot. Now, considering this, we calculate the exergy net rate of exergy carried into the heat exchanger by the gaseous streams, that is m dot a E f I minus E f E, and this is the working formula for the specific exergy. And similar way we can find out the net exergy carried by the heat exchanger through the water streams. So, calculating both the parameters, we can find out the rate of exergy destruction and subsequently exergetic efficiency for the heat exchanger. And in our vapor power term, we say it is a exergetic efficiency for boiler. And in similar way, we can model it for other individual components like turbines, then we have pumps. So, both of them can be modeled in a similar manner, but for condenser we think that this is similar to boiler, but with a little bit of difference. Here what happens, the working fluid enters to the condenser at state 2 and leaves state 3, and during this condensing process heat is being carried out by this cooling water, and this cooling matter. So, we say that m dot is the steam that is being or fluid that is being circulated within this vapor power cycle, and heat from this m dot fluid is being taken out by cooling water m dot C W, and which is entering at some state and leaving at some other states. So, we can do in the same way that when you say model this, stream 1 liquid 2 phase liquid vapor mixture enters and the condensate is existing, other stream can be separate cooling water is entering and exiting at known temperature and pressures. And again here also while modeling this, we assume that it is 25 degree centigrades and 1 bar. The similar way we analyze it for boiler, we can find out the exergetic efficiency for condenser. But for pumps and all, there are direct expressions which can be utilized that exergy destruction in the turbines based on the thermodynamic data at the states points. Okay. So, we will see how these formulas are being used while solving the problems. Okay. So, this is all about the exergy analysis. Now, we will move on to other vapor power cycles. So, the first segment of this discussion is that we need to talk about something on working fluid and organic cycles, organic cycle, which means that in a conventional systems where water is the main working fluid in a Rankine cycle, and there we use the concept like reheat, superheating, and with these techniques there are certain limit that we can go up to certain point, and that is restricted by the critical point, that is the peak point of this dome. So, we can keep on increasing the temperatures till we reach the critical point, but that critical point has also restrictions on the type of material that are being used. Now, to reach this critical point, many a times your working materials has certain metallurgical disadvantage or limitations. There will be thermal endurance of the materials for which we cannot go beyond this critical point. So, there the role of Rankine cycle is restricted only because although there is a thermodynamic possibilities that we can go up, but the material restrictions does not allow to go for this. So, in such cases what we expect is that we explore some cycles and which is operated as supercritical cycles. That means, instead of going through these domes, we, and for example, if you go for critical pressure of water, then you have to create an ambience of 22.1 megapascal or higher to go from directly from water to steams, but there is a restrictions that we cannot achieve this in a conventional through this conventional materials. So, for that reasons, if you want to go from liquid to steam directly without crossing this liquid vapor region, then we have to think of the cycle which is being operated on supercritical cycle. But there, to do that, your the material restrictions poses that some limitations, and because of which we have to choose some working fluids for which this critical pressure can be less. That means, we can operate Rankine cycle in a supercritical manner, that means directly going from liquid to vapor without going through this liquid vapor regions, and for that reasons what we have to choose is that we have to change our working fluids, and there are some substances, typically they fall under the category as organic substances. They are nothing but the mixture of hydrocarbons, refrigerants, ammonia or silicon oil, and such substance has the capability for going from liquid state to the vapor state directly without crossing these liquid vapor regions, and that too they can operate relatively less critical pressures. And when they operate relatively less critical pressures, then of course temperature goes down. Then in that way we can the metallurgical difficulties of materials is being taken care. And such cycles has many advantages, because they have a low boiling point which allows this Rankine cycle to produce power even from low temperature sources such as industrial waste, geothermal water, geothermal hot water and fluids heated through the solar collectors, but they have high cost per unit power, because they incur high cost per unit power as compared to conventional power plants, but the fuel cost is considerably lower. So, that gives rise to higher thermal efficiency. And of course, when there is a less fuel is used, so the supercritical plants have a less environmental impact. Then we will move on to another type of cycle, that is binary vapor cycles. So, here the vapor power cycle has the concepts that whether in a given cycle can you think of using more than one working fluid. So, if you want to see more than that, means we try to decouple the systems such a way that two turbines can be used, and each turbine will for each turbine the working fluid will be different. For example, a decoupled arrangement is shown here, and we call this as a binary vapor cycles. To understand this cycle, first let us see that what this means thermodynamically to us. In fact, here we draw the two domes, that is one dome for one working fluid, other dome for different working fluid on a single plot. So, if you see that one cycle operates in a one cycle, that Rankine cycle which operates as A, B, C, D, then A, that is in this cycle, and other one operates as 1, 2, 3, 4 and 1. Okay. So, we call them as a bottoming cycle, and other is called as topping cycle. So, basic difference between these two is that for both of them the common thing is that boiler unit and condenser unit. So, what it says is that for topping cycle, the condensing unit, that is from 2 to 3, state point from 2 to 3 will act as a boiler unit for the bottoming cycle, that is A, B, C, D, A. So, through this process what happens, the working fluid rejects the heat working film from topping cycle rejects the heat, and that is being taken by the bottoming cycle. So, considering this as a working model, thermodynamically we view, and here also you see that the power unit that comes as W12 one part and WAB as second part. So, there are two power turbines. So, here the thermodynamic model here looks like here that we have a topping cycle and we have a bottoming cycle. So, the bottoming cycle works as A, B, C, D, E, A, B, C, D, A, and which means that for the topping cycle condenser works as a bottoming cycle boiler, and both of them have a same unit, and two power units WT1 and WT2 comes into pictures. And here other feature is that for both of them you have a common steam generation unit, and in one case we say it is a conventional fuel based arrangement, other is we say it is a superheater systems. That means one case we can say the steam generation units consist of a boiler plus a superheater unit, and the superheater unit is for bottoming cycle, and the conventional cycle work on a topping cycle. Okay. Then there are this, and through this process what advantage we get, the combined cycle has higher average temperature of heat additions and lower average temperature of heat rejections, and of course thermal efficiency is greater from the either cycles. That means combined thermal efficiency is higher than that of either cycle. The next cycle that we normally use it for nuclear power plants. So, here the schematic diagram what we have is turbine, we have turbines, we have condenser, we have boiler. So, what happens is that here this work as a Rankine cycle using the common steam as a similar to the steam power plant. So, basically the reactor coolant gives heat to this Rankine cycle, and which acts as a steam boiler to produce the power. And since that means what we see is that we have a primary fluid which is water, and we have a secondary fluid which is circulated here, and the upper limit for this primary the upper limit for this working fluid would be T max. Now, we operate the Rankine cycle in a similar manner, because this heat exchanger unit we call this as a steam boiler for this Rankine cycle using water, and for the secondary fluid if you look at the temperature enthalpy diagram says that secondary fluid rejects the heat. So, its temperature falls down and it is being taken away by the steam, but one particular time we will have to see that what is this the curve looks like. So, there is a upper limit that the secondary fluid can work, and the temperature difference at one point which is in the saturated liquid dome, and that temperature difference is known as pinch point. So, we define a point which we call as a pinch point, which is specified such that temperature of the secondary fluid is slightly higher than the saturated temperature of the steam. This is one aspect. Other aspect is that permissible maximum temperatures, and that is restricted by the secondary fluid leaving temperature, and which is below the critical temperature of the steam. So, if you say that means if you say the temperature of water critical point is here, and this steam maximum operatable temperature would be somewhere below than this. And of course, the line, the slope of this line for the secondary fluid and the temperature enthalpy diagrams can be changed by considering the mass flow rate. So, if you are increasing or decreasing the mass flow rate, these lines can the slope of the line can be changed, and that again gives the judgment what should be the pinch point for the operational conditions. Then there is another concept called as low temperature power cycles. So, normally low temperature power cycles use different waste energies, renewable energies, and which involves similar way turbines, condenser, pump, and there is a low temperature source. And this low temperature source could be a solar pond, which means where the solar radiations are absorbed. Other can be a hot water from a geothermal reservoir, or it can be a considered as ocean thermal energy. And here the operating limits normally for this kind of applications is between 20 degree centigrade to 90 degree centigrade. So, obviously, we cannot use water as a working fluid for these cycles. So, we have to think about some kind of refrigerant like R134A is one such cases, and this can operate at pressure ratios in the range of 32.4 bar to 5.72 bar. So, this particular number tells you that by considering different refrigerant as a power cycle, one can think of Rankine cycle to operate in a low temperature power cycle. The last segment of this other vapor power cycle is something on cogenerations. Cogeneration is a concept where we say that two or more systems, power systems can be integrated together to have the need based applications. So, in this particular figure what it says is that a gas turbine power plant is integrated with the vapor power cycles. So, that means in a gas turbine power plant unit, whatever exhaust from the turbine is being utilized partially as a heat recovery steam generator unit. And here there are two power sources that comes in, one is gaseous sources, that means from the gas power plant, other is from the vapor power plants. So, here we say it is a steam or water, and here the working fluid is air. So, this is one aspect where two power plants are combined. Other way of looking at is extraction plant. So, extraction plant means that we have all come across the regenerative cycles, where we see that some part of steam is being extracted at some different states, some states of the during the expansion phase in the turbine. So, what we do is that we can think of meeting different heating loads in a flexible manner by extracting steams at different segment of the power plants. So, the such concept we call as a extraction plant. I mean here the it is based on application oriented. For example, we can extract some of the steam from a turbine and try to use it for some heating unit, for example, heating of water as one of the essential requirement for a community. So, this can also cater this particular concept also works in the mode of cogenerations. So, with this we complete our discussions on Exergy analysis and different vapor power plants. Now, we will try to solve a numerical problems based on our discussions for a vapor power system. So, the first problem here I am just taken the some schematic figure in which I have prepared a data sheets. What it means? We have a conventional vapor power systems operating water as a working fluid, and this it operates on a Rankine cycle, and the cycle has components like boiler, turbine, condenser and pump. And in our previous discussions we have done the complete cycle analysis, and for this complete cycle analysis based on the data given, one can find out all possible points for this cycle. So, that means first we have to use the operating pressures, and using the operating pressures and the condition of the steam at each component, and with the use of steam tables one can find out the thermodynamic states for each of the components. So, here the complete analysis has already been done. I mean, in one of the problems in our previous lectures we solved similar problems. So, here I need to summarize that when a vapor power cycle operates at these states, like state 1 which is nothing but entry for the turbine, and it is at saturated vapor at these conditions. That means, at this state we have 8 megapascal, 2758 kilojoule per kg enthalpy and 5.74 kilojoule per kg entropy. Similarly, for state 2 when it goes out, that means entry for condenser and exit for turbine, which is a liquid vapor mixture, and this is at lower pressure 0.008 megapascal, 1939 kilojoule per kg enthalpy, entropy as 6.2 kilojoule per kg Kelvin. And for all similar way, we have state 3 is saturated liquid and state 4 is almost pure liquid, that means subcooled region liquid. So, these values of pressure, enthalpies and entropies are given. Another additional information that we say is that the net output for the power cycle is 85. So, this is turbine work, we can find out 85 megawatt. Now, while doing this analysis, what we see is that we supply this Q in as a heat exchanger unit by using some combustion products, and we will see that how this combustion products is modeled. So, you can think of this particular boiler unit as a heat exchanger unit in which your one unit the combustion products comes at state 1177 degree centigrades, that is inlet state, and exit that goes out as at 527 degree centigrade, and this is at again 1 atmosphere. We say it is a heat exchanger unit, and that is modeled in terms of boiler. Now, while doing so, this releases heat to the steam which is entering in a counter flow manner. Now, here the water, that is at state 4 which is enters, and that state 4 is a liquid, and it goes as saturated vapor, and when it goes, this occurs at a pressure of 8 megapascal. So, this condition is at 1. So, here and here the main condition is that both the fluids they do not mix each other, and this heat exchanger unit can be models. So, for that reason, first thing that you to do that we need to find out for this steam flow rate what is the requirement for the combustion products, and here we can say that assume that it can be modeled as data from the air, and this air data we get for these conditions, and for which you have this entropy at inlet state and entropy at the exit state. So, a quick look of energy balance that gives that m dot A into Hi minus He plus m dot into H4 minus H1 is equal to 0. And here we say that this m dot A is for combustion product, m dot is for steam. Now, from these equations we can find a ratio m dot A by m dot is equal to H1 minus H4 divided by Hi minus He. So, the data from the data is rate 2758 minus 183 divided by 1457 minus 805. So, this ratio turns out to be 3.95, and since we know m dot, so we say m dot is 125 kg per second. So, that we get m dot A mass of air requirement would be 494 kg per second. So, this part once you do, then we are now prepared for the first answering the first thing, that is net rate of exergy carried into the heat exchange unit by the gaseous streams. So, let us understand our expressions for exergy analysis, that is if I write E dot F for air, that is nothing but m dot A E F A F I minus E F F E. So, this will be m dot A. We can recall our expression what is the specific exergy at inlet and outlet, that can be written as H I minus H E minus T 0 into S I minus S E. And since it is, we can model this enthalpy for air, so we can write H as C P times T for air. So, we know temperature, we know T I, so this will give you H I, and we know T E, this will give you H E. So, H I and H G we can calculate as H I is your 1457 kilojoule per kg, H G is 805. Of course, S I, S E and S I data is already given here. So, we can find out E dot F A is equal to m dot A, already it is 494, H I is 1457 minus 805, T 0 is 225 degree centigrade, that is 298 into 3.4 minus 2.7. So, E dot F A can be calculated as 219,040 kilojoule per second. So, approximately exergy carried by the air stream is into this heat exchanger unit or boiler unit is approximately 219 megawatt. And of course, this is being taken away by the steam. So, next part is for the steam. So, you say E dot F W, that is net exergy carried away by the water streams, that is m dot, here you have to use the mass flow rate for steam, and this is exergy of the steam at state 1 minus exergy of the steam at state 4. So, this is can be rewritten as similar way H 1 minus H 4 into m dot minus T 0 into S 1 minus S 4. So, we have all the data of enthalpy at state 1 and 4, entropy at state 1 and 4. So, this will give you exergy carried away by the water stream will be 125 into 2758 minus 183 minus 298 into S 1 minus S 4, 5.74 minus 0.92. So, this number is 142,375 kilojoule per kg. So, it is approximately only 142 units of exergy is being taken away. Then from this we can find out exergy destruction, that is E F air minus E F water. So, difference between these two is 77 megawatt. Then exergetic efficiency. So, epsilon B, that means for the boiler. So, it is nothing but m dot E f 1 minus E f 4 divided by m dot A E f I minus E f E. So, this number is ratio of 142 divided by 219. So, exergetic efficiency for the boiler is 0.64. So, approximately it is 64%. That means, boiler is you has used 64% of the exergetic efficiency. Then we will move on to turbines and pumps. For turbines, we can directly write down exergy carried in the turbine, that is E the exergy destruction for the turbine by simple expressions, that is T 0 into m dot into T 0 into for turbine state is S 1 minus S 2, that is S 2 minus S 1. So, S 2 minus S 1 we can m dot is 125, T 0 is 298 and S 2 minus S 1 is 6.2 minus 5.74. So, this will give you for turbine exergy carried by the fluid in the turbine or exergy destruction in the turbine as 17135 kilojoule per second. So, approximately 17 megawatt. Remember, this is the exergy destruction, and if you calculate exergetic efficiency for epsilon turbine, that is nothing but your WCV divided by m dot or like W cycle divided by W dot cycle plus ED turbine. So, this is in our cycle it is 85, will be 85 divided by 85 plus 17. So, the ratio will be 83%. So, exergetic efficiency is 83%, which is quite good. And similarly for pumps, and in the power plants the pumps normally takes the least energy or negligible energy. So, just for the sake of calculation, if you just try to calculate exergy destruction for the pump will be m dot T 0 into S 4 minus S 3. So, as per the numbers you can say this number, the entropy difference is quite low. So, it is 125 into 298 0.92 minus 0.9. So, this number turns out to be 3.7 kilojoule per second, which is quite low or approximately 0.003 megawatt. That means, pumps take least energy. So, of course, if you say exergetic efficiency, it is almost nil, negligible. Then we will move on to last component, that is condensing unit. So, in a condensing unit one can think of this modeling as, because if you look at this condensing unit, there is a separate water stream. So, in which we have the steam or which is liquid plus vapor mixture enters at state 2, and here condensing steam, that is leaves at state 3. This is saturated liquid, and here this is giving heat to the cooling water. And the data sheet for this cooling water is that cooling water enters at 38 degree centigrades and leaves at 18 degree centigrades. This mass flow rate of this cooling water, which is given here as 2500 kg per seconds. So, this analysis will be modeled by similar way the way you did it for boiler. So, one can write out the first term, that is net exergy carried by the cooling tower. So, we say E dot F cooling water as m dot Cw into EFE minus EFI, that is m dot Cw He minus Hi minus T0 into Sc minus Si. So, by inserting the number, what we write, 2500 kg per second multiplied by, since it is water, H can be modeled as Cp times T. So, it is 4.2 into temperature difference 38 minus 18 minus 298, entropy data will give you 0.5 minus 0.22. So, E dot F for cooling water would be approximately 1400 kilojoule per second or close to 1.4 megawatt. Then next term we say we need to find out exergy destruction. So, exergy destruction we can write down as ED as T0 into sigma Cv, and this is nothing but control volume for the condenser unit. So, that can be written as T0 times m dot S3 minus S2, that is combined effect of steam as well as the cooling water. Cooling water is m dot Cw into Sc minus Si. By inserting this number, we say exergy destruction as 298 into 125 for steam, that is 0 point difference is entropy difference is 0.9 minus 6.2, then plus 2500 into 0.5 minus 0.22. So, by calculating this number, we say the exergy destruction is 11175 kilojoule per second. It is approximately 11.175 megawatt. So, exergy destruction in the condensing unit or condenser is 11.175 megawatt. Then we are now able to find out the exergetic efficiency for the condenser. So, we say epsilon C as T0 into m dot S3 minus S2 divided by T0 into m dot Cw minus into Se minus Si. So, this is nothing but these two separate terms which is calculated in this in the exergy destructions. So, this number when you insert, it is 197,425 divided by 208,600. So, so you say exergetic efficiency per condensing unit is about 0.94 or approximately 94%. So, it means that we have the this gives you the combined effect of a vapor power systems, whether we are this complete power cycle integrated with dead state at P0 and T0, this combined systems has efficiency we can find out for component wise as well as the when they work together we can find out the component efficiency of component exergetic efficiency of each component when they work together. So, with this I conclude. Thank you for your attention.